So we finally start our tour through all of the different dinosaur taxa that have been described. And as I said before in the previous lecture, we're going to continually refer to the cladogram from your book to organize our thoughts. And so again, every one of these red dots is a node defined by particular features. Everything above the node has it. Everything below it does not. And we are going to start with this side, the right side, and the ornithischians. So remember the ornithischian hips. Now, the first branch coming off of here is this weird group called the Fabrosauridae. They're very rare and still oddly known, and they've been kind of placed in other spots depending on different authors. So we're going to emphasize the next node up, which is the Thyreophora right here. And the Thyreophora are going to be two different groups, the Ankylosaurs and the Stegosaurs. So just a slide explaining what's going on. These things, the Thyreophora, are the dinosaurs that are covered or have at least somewhere on their bodies skeletal armor. They have grown larger, thicker plates of bone that is used to cover certain parts of their bodies. As I said before, the two major groups, Ankylosaurs and Stegosaurs, and there they are. Ankylosaurs typically have armor all over their body, usually on the dorsal side. Sometimes the head is armored, sometimes it is not. Whereas Stegosaurs have the rows of plates over their dorsal backs right here. Again, this is just saying, reiterating again how to read a cladogram. I'm sure you're good with it by now. Another one here, etc., etc., etc. You see, I'm definitely going to be emphasizing the cladogram for us here. But let's first talk about a group that's a little bit different. There are two primitive Thyreophores. They don't really fit into the Ankylosaurs, and they don't really fit into the Stegosaurs. That's why we just give them the weird grouping, the primitive Thyreophores. Are they truly ancestors to those other two groups? We're not really sure. So let's look at them real quick and dismiss them. They are both Jurassic creatures. Notice that one, the Scelidosaurus, is much larger than the other one. And again, you've got the sort of laying out of what their different armor presence is. Note here as well for Scelidosaurus that it says that it has simple leaf-shaped teeth. Keep that in mind when we're going to see a couple pictures of these things later in this lecture. These types of teeth are typically taken to be an early dinosaur characteristic for vegetation processing, being an herbivore. So here they two are, the Scelidosaurus, the Scutellosaurus. Scelidosaurus, of course, here you can see all of these little round polygons sort of going down the back and down the tail on the top and on the bottom, and then sort of floating on the sides here. These are the armor plates all over the body of this creature, and notice that there is no armor on the head. The Scutellosaurus, they didn't even bother to draw it here, but it does have an extensive cover of bony armor plates. Now, one thing to look at here is that the forelimbs for both of these creatures are much shorter than the hind limbs. And so for the Scutellosaurus, it's kind of shown here in a bipedal or standing mode, whereas in the Scelidosaurus, this is shown still in a quadrupedal mode. We don't know, and as you're going to see in just a couple seconds here, different artists have taken this data and kind of run with it both ways. So artist renditions, now that we're talking about dinosaurs themselves, We're going to hit a lot of different ways in which artists have fleshed them out. And as I'm going to reiterate over and over again, typically the musculature, the stance, all of those things, we have good reason to do the reconstructions that are done because we can guess this very well from the bones. Color and superficial things like that and sound, etc., it's mostly guesswork. Okay, so let's look at these two things. Both Scutellosaurus and Scelidosaurus have been the subject of a lot of artists' renditions because they are common in Africa, and in Africa a lot of places will put these on their stamps. So here's this Scutellosaurus, and then here is Scelidosaurus. You can see they had the Congo, Liberia, Tanzania, and you can see the different sort of arrays of armor plating on this thing. Interesting group. Well, let's look at a more detailed cladogram. For every cladogram, you can always make one that is more detailed, that is more specific. And here's a cladogram of the Thyreophora itself. The same rules apply. Everything above any particular node has all the characteristics that define the node. And so here are the Thyreophorans, and then they're branching up. Here's the primitive Thyreophorans, and now they're going to go over here to the Ankylosauria proper, and there's going to be two groups here, and both of these are going to be families. The Nodosauridae, we call them the Nodosaurids, and the Ankylosauridae, we call them the Ankylosaurids. Scutellosaurus and Scelidosaurus, they're over here, and now we're looking over here first. So just the facts here about the Ankylosauria. The name literally means the fused reptiles. Whole bunch of things to look at here. First of all, they do have those leaf teeth again. They have broadly arched barrel-shaped bodies caused by the curvature of their ribs around their internal organs. And then, as I said before, they're mostly covered by armor on the top. They have hooves on their feet, and all of these are herbivorous. That goes back to these leaf teeth here. Two different families, as I said before, the Nodosaurids and the Ankylosaurids. And now, don't get confused, although you know it's probably likely going to happen. You're going to see a lot of words that are similar. So there's Ankylosauria, that's the node. There's the family Ankylosauridae, that's a branch off that node. There is a genus Ankylosaurus, which is one of the genera within there. All of those things look similar. They all have the same root, but they all mean different things. And yeah, it's going to be important. Let's look at the Nodosaurids first. There's the stats on them. Europe, North America, one in Australia. Very, very small skulls. No armor or horns, but there are spines in the armor. There is no club at the end of the tail. So that's a key thing right here. And notice again, here's the genus Nodosaurus in the family Nodosauridae. Makes a difference. If we look specifically at Nodosaurus, we don't really have good skulls. We have some spine areas. They have basically a toothless beak, a front end of the face, and then the leafy cheek teeth. Pretty big size here. And again, the hind limbs are much greater than the forelimbs. That just leaves the Nodosaurids alone, but now let's look at the family Ankylosauridae, a much more abundant group. A lot of things to note here. First of all, they are late to the game. They are present only in the Cretaceous. They do have some holes in this armor in their skull, but otherwise they've got some heavy armor over the skull. They're not spiny, so they don't have spines like the Nodosaurids. They're more plates of armor. And then they are most known for their large club at the end of the tail. So this is 2 giant armor plates. And look at the scale bar here. That's a meter. So you've got a meter of solid bone that presumably they use to swing around and deter predators, potential predators. What are the relevant natural selection options or pathways for these things? They've been called the Mesozoic tanks, so there was basically natural selection for defensive armor. So they're clearly not speedy creatures. They are passive herbivores, and they're so armored up that they were probably relatively invincible except to the largest, most determined predators. You can see here their jaws with their teeth in there, and there's what we call a leafy-shaped tooth. Leafy because it has all these sort of invaginations of the teeth here. And so you can picture fronds of vegetation going through here, biting down and sort of snipping these things off. What was their defensive method? If they're sort of naturally selected for defense, squat, dig, swing that mighty club. And in the module and canvas, besides the notes set here, I've also included 2 different articles for relevant recent finds as far as the Ankylosauria are concerned. The first is a remarkably well-preserved ankylosaur. It's actually a nodosaur from Canada. Beautiful, beautiful preservation on the thing. And then the second is ankylosaur that's unnamed so far, but it's from China, and it has good evidence showing this sort of dig a trench, dig a hole, squat down in it behavior. Here's another sort of larger view of the club. You can see, first of all, these fused vertebrae here. So the last part of the tail, these vertebrae are all fused together. So it's sort of a solid stick. And then here's the armor plates fused together for this large club at the end. And again, here's just another view of these things, both lateral and dorsal view, so you can see it. An important distinction between ankylosaurs and nodosaurs deals with their skull and their pathways through their nasal passage down through the sinus cavities in the mouth. The nodosaurs have a very simple sort of throughway, straight through, as shown here on the left. Ankylosaurs have a very sharply turning, curving what we call an S-shaped pathway, and a dense honeycomb of complex sinus cavities. Perhaps they have some supplemental bones in there called turbinals, which mammals have, which leads some people to think that these might have regulated their body temperatures similarly to mammals, but the jury's still out on that. Why would they have this? Why would the difference? Who knows? But many hypotheses have been thrown out there, and you see some listed there below. So that's it for the ankylosaurs. Let's look at the other side of that cladogram, the stegosaurs. These are the plated lizards. And now this is going to include another sort of dichotomy. There's one family, the Stegosaurids, and then one other odd animal, this Wangosaurus. Rather large thing with spines that are spine-shaped armor, not big broad plates, but spines, and these are traveling down the dorsal side of the spine. So on the cladogram, we are looking at this branch here, the Stegosauria. If we look at the Thyreophora, more detailed cladogram, you see there's the branch for Stegosauria, and then we have the Stegosaurids, and then we have this one oddball here. Now remember, this one has spines on its dorsal vertebrae. This one has large, wide plates on there. Let's look at this again, just the relevant facts about this beast. And here's an image of it, and you can see the several large plates, but they're spiny shaped down the back of the creature. Just artist's rendition for these things. And here you go. Here they fleshed it out more with all of these elaborate spines over here. So you see, it's not really an ankylosaur, and it's not really a stegosaur, but it has more characteristics that it shares with stegosaurs than ankylosaurs, so it is branched off with those. As far as the rest of the stegosaurs, this is all of the rest. A lot of very distinctive things about them. They have these low skulls and long snouts. They have an elongated face. Their eye sockets are located towards the posterior, meaning they're behind the last tooth in the cheek teeth row. Our eyeballs, our eye sockets, are right above our cheek teeth. And so in an elongated face, you have the teeth sort of stopping before it reaches the same plane of the eye socket. The hind limbs, again, longer than the forelimbs, and there's hooves on the end of the toes. Let's look specifically at the genus Stegosaurus, and then 2 stars, the midline row of large armor plates and small plates elsewhere. They also have the leaf-shaped teeth. They have a relatively long neck compared with the ankylosaurs, which really had sort of a linebacker type build, a big head sort of sitting right on shoulders. Interesting little group here, Stegosaurs. A couple of pictures, sort of first a partial view of the skeleton laid out in reconstructed form, and then an artist's rendition of the thing. And the forelimbs here are drawn as nice straight up forelimbs, and even in this artist rendition here, but the more proper orientation that we think of now is that it was sort of a squat thing, that these elbows would have been more bent, and the face and the front end directed even more down into the vegetation. We are very certain that it did not have one solitary row of plates in sort of a mohawk fashion. They simply don't fit. Whenever we find articulated specimens of these things, and the next slide is going to be a picture of it, it doesn't really tell us, but if you just kind of line them up, and if you put them end to end to end, they're far longer, there's far more distance here than there is distance over the body. So they probably had 2 rows which were slightly offset, like this. This perhaps would have been optimums for some sort of thermoregulation, cooling, etc. So basically, if this got wet, you could orient it into the winds. The blood flowing through the plates would cool. It could also heat the animal up. In the morning, it'd sort of wake up. If it's colder, a little bit cooler, to heat the blood up and make this animal active, you could turn towards the sun, perpendicular to it, and sort of operate these things like a solar panel to heat up, perhaps. A view of a great specimen. This thing is preserved in wonderful condition. Most of the skeleton is there. This would be considered articulated, but how these plates were oriented, you can't really tell by looking at this. It could be anyway. Let's examine a little bit about stegosaur paleobiology. We have a lot of specimens of these things, so we can speculate at least about their paleobiology. Let's talk about the plates first. I already mentioned this, that perhaps there was some sort of thermoregulation effect, or defense against predators. For these creatures, terror is going to come from above. A bite is going to come down from the larger predators like Allosaurus around them. And perhaps that's good. I mean, it would certainly baffle a bite. But those plates are pretty blood-filled, a lot of venation, going through these things. And so you don't want to stick something that's filled with your blood supply, a significant percentage of it at any particular heartbeat, upwards where it's going to be bitten. So maybe yes, maybe no. It's tantalizing to say that the earliest stegosaurs, which had spikes, had these things for natural selection against defense against predators, but then natural selection operated on those features to make them wider and flatter to adapt them for thermoregulation. Who knows? And again, just a couple pictures here. Here's some early stegosaurs with more spiny like plates, and then Stegosaurus proper with the big, wide, flat plates. As far as their lifestyle, they were probably very slow, methodical vegetarians. They were quadrupedal, and as you see here, they're sort of butt in the air, face down in the chow, foraged for vegetation, very low. Biogeography. They originate in the Middle Jurassic in China, but wow, by the late Jurassic, they are found virtually everywhere. They don't make it quite that far into the Cretaceous before their diversity gets greatly limited, and they linger around until the latest Cretaceous when there's just a couple of genera, a couple of species left, and that's it. This decline in this from the Jurassic into the Cretaceous, particularly in the Cretaceous, we think is tied to the change of vegetation that happens over the Earth then. The type of plants that existed in the Jurassic were mostly gymnosperms, pines, other evergreens, plus ginkgos, a lot of tree ferns, things like that. And they get largely replaced by the evolutionarily superior angiosperms, flowering plants, in the Cretaceous. And as the number and diversity and abundance of angiosperms rose in the Cretaceous, the diversity and abundance of stegosaurs and a bunch of other dinosaurs declined. And so perhaps it's a case of a wedge type thing where there simply is one group that increases in abundance at the expense of the other. Finally, we can't really talk about stegosaur biology without talking about their noted reputation for being, well, slow-witted, dim-witted, dumb. This cartoon says it all, and it talks directly to their cranial capacity, which we can talk about. We don't have preserved brains, but we do have enough skulls that we have preserved casts of the inside of their brains. And the one thing you can say about them is that they are typically reptilian. There's no big curvature to the cerebrum, so not brainiacs here. Very small cerebellum, a rather large medulla. And so these were sort of instinct-driven creatures, not creatures sort of imbued with great critical thinking capacities. Huge olfactory bulbs. Look at the front end here of this. This means that their sense of smell was very great. This is probably how they sort of discriminated their different food sources. How big were their brains? Well, if you take one of the skulls, pour water into it or sand or whatever, and then pour it out and measure it, you can get a volume. And so for Stegosaurus, about 50 to 60 milliliters. If you took a living lizard and scaled it up to the size of a stegosaur, their little brains would be about 110 to 120 milliliters. So Stegosaurus, small. A house cat, a little teeny tiny cat, is about 30 milliliters. A walnut. People always used to say, oh, their brain was the size of a walnut. Well, a walnut is about 15 to 20 milliliters. So, yes, stegosaurs were not brainiacs. They do have one of the smallest brain volumes to body size ratios of any animal that ever existed on planet Earth. But they were successful. They lived millions of years without necessarily needing great cranial capacity. Sometimes people bring up the whole idea of a second brain. That's probably not true. At the base of the spine, near the hip, there's an enlarged spinal cavity. It's actually a little bit bigger than the cavity for the brain in the skull. Did it control the rear body? Did it store extra tissue or fat or sugars or whatever? We don't know. We just don't know. The plates themselves, were they stationary, basically stuck up there forever, or could they move? Mammals today, like we, humans, have various skin twitching abilities. So humans, we can do it on our face. Birds can flip their feathers around. Some reptiles can adjust their plates, or they sort of fast twitch their skin around their throats and backs. Stegosaurs, well, maybe. And so in this artist's rendition here, you see the little stegosaur sort of flipping its plate around, moving it back and forth, twitching it around. And then I like this artist's rendition here. Here's a large carnosaur coming up to this stegosaur, limited in brain power as he was. He has an array of defenses. And look at this designation here, a 5-ton ballet dancer with armor-plated tutu of flipping bone triangles and a swinging spiked war club. The stegosaurs would not just be completely weak prey in this scenario. And that ends our discussion of the Thyreophora.